Welcome to the 15th lecture on Amdahl's law. So, till previous lecture, what we have seen that how we can summarize all the results and then coming up to a particular solution. Now, we will see another law that will tell us little more about what we have learned. So, Amdahl's law was established in 1967 by Jean Amdahl, and what it gives is that it provides an understanding on scaling limitation and economics of parallel computing. So, by scaling limitation we can understand that the transistor size is becoming smaller and smaller. So, it gives an understanding on scaling limitation and also on the economics of parallel computing. By economics of parallel computing, what we mean is that suppose today we have quad core, we have multi-core technologies. So, when you are investing or when you are having so many cores, are you getting the return? When you are having just one core, how much was your performance? By having more number of cores, are you really getting that advantage that you are supposed to get? So, are you getting that return out of it? So, it also gives us the economics of this parallel computing. And of course, it forms the basis for quantitative principles in computer system design. So, we can actually in a quantitative fashion can tell about the design principles of a computer system. And Amdahl's law is not only for computer system design, it can be applied to other applications as well and for other domains. Let us see what exactly is Amdahl's law. It is basically used to find the maximum expected improvement of an overall system when only part of the system is improved. What do you mean by this? What we mean is that suppose overall system, we have full overall system, but maybe part of which, let us say only 40% of that part, that whole part, we can make an improvement. So, we want to see that by making 40% of the part improved, how we can get an overall improvement. So, I will just give you a small example. Let us say you want to travel from place A to place B. So, let me take an example. So, I want to travel from A to B, and you have a middle point because you have to travel through this point, you have to reach this point, and from this point again you have to take. Now, from this part to this part, let us say for traveling, you can only have the travel, you can only make through taxi and there is no other way. But for traveling from A to X, you can use many modes. One is taxi, one is train, another is by air. So, what you can basically do is that you cannot do anything for this part. This part is limited by the speed of this taxi only. But all we can do is that we can improve this part, that is from A to X, by either using taxi, either using train or by air. So, this is where we will have to see that how can we optimize. We need to reach from A to B through X, and then only I can improve this part, not this part. This part will be same. But by improving this particular part, how much improvement we are getting out of it, that we want to see. So, that is what Amdahl's law comes into picture. So, it can be used to find the maximum expected improvement of an overall system. We will see the improvement of an overall system when only a part of which is improved, because another part we cannot improve it. It basically states that the performance improvement to be gained from using some faster mode of execution is limited by the fraction of time the faster mode can be used. Okay. So, this again coming to in terms of execution of some instructions. Okay. So, what by this what we mean is that as we are saying that this we are actually improving a fraction of the part, and fraction of that particular part can be used more, then the overall improvement can be further increased. So, very useful to check whether any proposed improvement can provide expected return or not. That is what I am saying, that let us say I put some improvement on that particular part where I can improve, but by putting improvement on that particular part, will you actually get that return that you are expecting, or you will not be able to get that return, or how much return you will be able to get. So, all these things can be determined through this Amdahl's law, and it is used by computer designers to enhance only those architectural features that result in reasonable performance improvement, and this is referred as quantitative principles in design. So, again by this what we mean, let us say we might have an adder, a multiplier, and such in general purpose computing we may say we are using adder more than multiplier, just as a case I am just saying. So, in such cases what can happen, if you try to improve the multiplier which you are not using much, then it will not give you that particular kind of improvement. So, that is also what you have to look into, that we are improving a part which is also used more number of times. The number of times it is used is more, and we are improving that particular part. So, where we can get overall improvement much more. Amdahl's law demonstrates the law of diminishing return. So, what is that? Let us take an example. Suppose we are improving a part of the computer system that affects only 25% of the overall task. So, out of 100%, only 25% of the work can be improved. The improvement can be very little or extremely large. Let us say how. With infinite speed up, so only 25% of the part can be improved, and we are saying that if we make that 25% part task can be done in 0 time, maximum that much improvement can be done that it will take no time to finish that 25% of the task, but we cannot do anything with the 75% of the task. 75% of the task remains, but only that 25% of the task we are making some improvement. And what kind of improvement? We are saying that we are keeping that time 0. So, in no time that particular task can be performed. So, maximum possible speed up can be execution time original divided by execution time new. So, as the original execution time, let us say it is 1, what will be the new execution time? Out of total 100% of the task, 25% of the task can be done in no time. So, you can just take out that 0.25 which is coming to 1.33. So, we can have a maximum of this much improvement if you can improve that 25%, and we can say that the 25% of the task can be done in no time. So, we can never get a speed up more than 1.33. Even if you do whatever you want, we cannot get an overall improvement, because we can only make that 25% faster, because 75% still is working at a previous speed. So, Amdahl's law actually concerns the speed up achievable from an improvement in computation that affects a fraction f of the computation, where the improvement has a speed up of s. So, on this fraction f, we are having an improvement of s. So, total, this is the f portion and this is 1 minus f. So 1 minus f, there will be no change, and we can only have a speed up of s to this f portion, fraction, this fractional portion. So if you can reduce this, so it will reduce by, it will become f by s. So earlier it was taking this much time and now it is taking this much time. So after improvement, we can execute the same task by this percentage. So let us find out how we can find out the overall speed up. So execution time before the improvement is 1. This was fractional part and this is 1 minus f, basically this is 1. And what is the execution time after improvement? We have seen 1 minus f will remain as it is, and we have to make improvement on f. So it will become f by s. So speed up will be 1 execution time old divided by execution time new, that is execution time after the improvement. What it is? This is 1 minus f plus f by s. This is what we have got. So as s tends to infinity, speed up will actually, this, if you make this part 0, so what will happen? The speed up will be 1 divided by 1 minus f. That is what we have seen in the previous slide. So the fraction f actually limits the maximum speed up that can be obtained. So we cannot make further because it is said that only fraction f can be improved. If fraction f can be improved, we can make the maximum achievable up till with that fraction f. So let us illustrate this law of diminishing return for f equals to 0.25 by changing the value of s. So speed up is 1 divided by 1 minus f plus f by s for various values of s we have computed. So let us say when s is 1, we are getting a total speed up of 1.00. When it is 2, we are getting 1.14. When it is 5, it is 1.25. When it is 10, it is 1.29. So the difference, if you see, it is basically reducing. This difference was more, this is less, this is less, this and this is even less. And what we can see is that after certain amount of time, that is after certain speed up, we are not getting any further speed up. The speed up is limited by a factor of 1.33, because we have already said we can get a maximum speed up of 1.33. That is what we are getting, even if you are increasing this fractional speed up by any amount. So unnecessarily it is no point increasing this speed up, as there is a limit to it, because the maximum speed up that can be achievable is 1.33. So let us take another example where f equals to 0.75. This table also shows the speed up for various values of s. As we increase s, what it depends on how it affects the overall speed up. So again we see that when s is 1 lakh, then the speed up is 4, and the maximum achievable speed up when the fraction is 0.75 is also 4. So even if you can increase, if you increase this s, this will remain the same. So these are some design alternatives using Amdahl's law. What we are saying that, let's say we have a portion of a program. This is loop 1 and this is loop 2. This loop is of 500 lines and this loop is of 20 lines. But this 500 lines of code, it takes 10% of the total execution time, only 10% of the total execution time. What do we mean by that is that this takes certain amount of time to execute, but this particular loops is only taking 10% of that total time, and this loop 2, which is only 20 lines of code, but it is taking 90% of the total execution time. Although this is small portion, but that small portion is taking more amount of time. So we need to also take into consideration this design alternative. So let us see if we make some improvement on this particular case, where only 10% of the total execution time is used for loop 1 and 90% of the total execution time is used for loop 2. How do we get? So let us say we make 10% of the program 90 times faster. So how much speed up we will get? So this is 10% of the program you are making 90 times speed up. So 1 divided by, this is 1 minus f, and this is f by s, where f is 0.1 and s is 90, because we are making 90% speed up on this. And what we are getting? We are getting a value 1.11, the overall speed up. Now we make 90% of the program 10 times faster only, but that portion is 90%. So 1 divided by, this is 1 minus f, this is f by 10, and we are getting 5.26, which is much more, but we are only making a speed up of 10 times. So making 10 times speed up of a portion which is used most amount of time, which is taking more amount of time, that is 90% it is taking, that will giving a better result. Similarly, make 25% of the program 25 times faster. So 25% we are making 25 times faster, and this remains 1 minus f is 0.75. We are getting this much. Similarly, 50% of the program making 20% faster. So this is giving 1.90. And if we make 90% of the program 50 times faster, we are getting a value where we are getting maximum, because this is 90% of your program, we are making a speed up of 50%. So where you are getting a value of 8.47. So this is how you can see that if you are making improvement on a part of your program which is used more number of time, that will give a better speed up. Let us take another example. Suppose we are running a set of programs on a RISC processor for which the following instruction mix is observed. So we are having load, store, ALU and branch operation, various kinds of operation that are there, and this is the frequency at which load instructions are taking place. This is the frequency at which store instruction is taking place, and so on. And this is the CPI, cycles per instruction for load, cycle per instruction for store, and ALU and branch. Now let us find out WI into CPI. So we multiply this into 0.2, we get this into 0.08, we get this, and so on. Now percentage time it is used can be found out by total CPI. Total CPI will be 2.08. So if total CPI is 2.08, we will divide 1 divided by 2.08 to get this. This divided by 2.08 we will get this, and for this as well as for this. So what we do, this is the given thing, and we have found out Wi into CPI and also the percentage time it is used. Now we carry out some kind of enhancement, and now we will see what is the improvement that we can get. So we carry out a design enhancement by which the CPI of load instruction reduces from 5 to 2. So earlier this load instruction was taking 5 CPI, now it will take 2 CPI. So what will be the overall performance? Now we want to see the overall performance that we will get. So how do we get it? So fraction enhanced f is 0.48. So we can see that we are reducing from 5 to 2, this. So fraction which we can actually enhance is 0.48, and the unaffected portion will be 0.52, 1 minus f. So if f is this and 1 minus f is 0.52, what will be s? Earlier it was 5, now it has become 2. So this speed up will be old divided by new, which is coming to 2.5. So if we just put it in this value 1 minus f plus f by s, we get 1.40. So therefore the speed up will be 1.40 with that enhancement. Similarly, we can solve this using the other way. What is the other alternative? Let us just go back to 2 slides and figure out. We have found out the CPI, that is 2.08. Now we will make an enhancement, make this as 2, and then we will calculate the CPI once more. So let us see how to do this. So old CPI was 2.08, and the new CPI we will same way do 0.20 into 2 plus 0.08 into 3, these will remain same. So the new CPI that we have found out is now 1.48. Earlier it was 2.08 when for the load instruction the CPI was 5. Now we have made some improvement and made the CPI 2, and we have figured out the new CPI is 1.48. So with this, what will be the speed up? As we know that speed up is execution time original divided by execution time new. So the formula of execution time, if we recall from our previous lecture, it is instruction count into cycles per instruction, here in this case will be old, into the cycle time, CCT, or the period we can say, and same way IC into CPI new into C. We can just cancel out the other things. What are these two? This is 2.08 divided by 1.48. So we are getting 1.40. So either way if we do it, we are getting 1.40. So these are the two alternative ways through which you can perform this. Let us take another example. So in this example, what we are saying, the execution time of a program on a machine is found to be 50 seconds, out of which 42 seconds is consumed by multiply operation. So most of the time multiply operation is taking more time. It is required to make the program run 5 times faster. Okay, so the overall speed up of the entire system, you want to make it 5 times. By how much speed up of the multiplier? By how much must the speed of the multiplier be improved? So let us say it has been given that you want this 5 times speed up. So how much this multiplier part can be improved? So we will just put that in the formula. F will be 42 by 50, that is 0.84, and according to Amdahl's law, speed up is given 5 will be equal to 1 divided by 1 minus f. 1 minus f will be 0.16, that is 1 minus 0.84 plus this fractional part where improvement, how much improvement is required. So, I am doing dividing that by s, because we need to find out this, how much speed up on the multiplier you have to do such that the overall speed up is 5. So, I solved this equation. If you solve this equation, you will get s as 21. So, you have to make a speed up of 21 times to the multiplier so as to get an overall speed up of 5. So, this is how this problem can be solved. Let us take another example. It is the same example, but I want to make it more fast. The execution time of the program on the machine is found to be 50 seconds, out of which 42 seconds is consumed by multiply operation. It is required to make the program 8 times faster. So, similar way, earlier it was 5, now it is 8. I put it 8 and I try to solve it. And what I get? I am getting a negative value. Why I am getting a negative value? Okay, so we need to see that can we at all make 8 times faster, because there is a limitation of something, that how much part the enhancement can be performed. So, in this case we can see that 1 divided by 1 minus f, that is 1 divided by 1 minus 0.84 is 6.25. So, the maximum achievable speed up is 6.25 and you are saying you want to get 8. That is not possible. So, in this case you cannot have a speed up of more than this achievable speed up, as we have already seen that earlier. So, no amount of speed improvement in the multiplier can achieve this. Let us take another example. Suppose we plan to upgrade the processor of a web server. The CPU is 30 times faster on search queries than the old processor. So, the CPU is 30 times faster on the search queries than the old processor, and the old processor is busy with search queries 80% of the time. So, the old processor was always busy 80% of the time with the search queries only. Estimate the speed up obtained by this upgrade. So, we are making an upgrade of 30% on the search queries, and the old processor was using 80% of the time that search queries. So, it will, your f will be 0.80 and 1 minus f will be 0.20. So, you substitute in this particular equation in the speed up and you get 4.14. So, with this upgrade we can get the speed up of 4.41. So, in this lecture we have seen what is Amdahl's law, and we have also seen that how the speed up, maximum speed up can be achievable through this Amdahl law. And we have also seen that while designing certain system, you have to take into consideration that speed up, if the speed up is not can be made on the entire system, it can be only made on the part of the system. We need to analyze that only that based on the part of the system, how much overall speed up you can get, because a part you cannot do anything, only a part you can make the improvement. So, Amdahl's law actually states that on the part where you are making improvement, how much maximum speed up you can make, that is the overall speed up you can achieve. Thank you.